Wonderful. Um, Hi, everyone. Thanks for joining us for the 2024 ISAR Virtuaeolian Seminar Series. Philippe, Andrew, JB, along with the rest of the ISAR board members are excited to continue the Virtuaeolian tradition with Marine today. Before I turn it over to Philippe to introduce our speaker, we just want to provide a structure of today's webinar. Please keep your microphone off unless it's your turn to speak during the Q&A session of the event. But please feel free to type questions in the chat at any time. We will wait till the end to read them aloud. During the Q&A, you can also just raise your hand if you prefer to speak. This meeting is being recorded and will be shared with the ISAR community. So please hang with us until the end, as we have also some announcements to make. And we ask everyone to work to contribute to creating and maintaining a welcoming, respectful work environment that fosters diversity, inclusion, and belonging. And with that, I will turn it over to Philippe.
Okay, thank you, Madi. Hello, everyone. And we are very pleased today to welcome Dr. Marine Poizat. So, Marine, you did your PhD on snow dunes, and this is going to be the subject of your talk today, obviously. And so this PhD was at the Institute for Geoscience and the Environment in Grenoble, in France, under the supervision of Ghislain Picard. And I must emphasize that you did some field work in Antarctica for 3 months. This is rather brave, I would say. And and you defended your PhD recently, the last August. So and now you're just starting a postdoc at the Geological Survey of Finland to work on sediment transport and bedforms on the seafloor of the Baltic Sea. Including measurements with a benthic lander. So it seems that you like very remote and inaccessible places. Maybe when we need someone to study the dunes on Mars or Titan, we'll send you then. But for the moment, we will focus on snow dunes. And which at the same time, I like this subject because it's dunes. It sounds familiar, but snow dunes sounds unusual. So I'm very glad to listen to your talk with this mixture of usual and unusual objects. Thank you, Marine. The floor is yours.
Well, thanks, Philippe, for the introductions, and so thank you everyone for being here. As Philippe said, I'm going to talk about snow dunes in Antarctica, and I'm going to focus on 2 types of dunes, snow barchans and snow linear dunes. And as you may have noticed, snow dunes are largely understudied and misunderstood. So I will rely on the advanced knowledge on sand dunes to get more insight into the snow dunes distributions and dynamics in Antarctica. But before getting into these bedforms, let's talk a bit about Antarctica. So what you're looking at is an example of the surface of Antarctica, and we can see that we have a lot of different features, and that the surface is absolutely not flat. And actually, Antarctica is the perfect continent to study snow bedforms. And it has a very particular topography with a flat inland. So when I'm talking about the inland, I'm talking about the regions which is above 2,000 meters. And if you see my mouse, it's this region is located roughly over here. And we got steep coast and a flat inland. And this is impacting the wind regime. And what we're looking at here is a map of the wind roses. So it gives both the wind speed through the colors and the wind directions through the spread out. And if we look at the inland, we can see that we have many blue wind roses. So we have low wind speed with annual mean around 6 meters per second. And the wind roses are really spread out. And this is very visible under this red dashed line, which I will be referring to as the ridge after. And if we look at the wind roses, we can see that the wind is going pretty much in every direction. So over the inland, we have low wind speed and multidirectional speed. But if we look at the coast, then we can see that we have more unidirectional winds and we have higher wind speed with a mean wind speed up to 16 meters per second. So we have this contrast between the inland and the coast, which is also visible on the precipitations. So here we can see that we have dry inland with precipitation down to 30 millimeters per year and wetter coast. And this is also visible on the temperatures with a cold inland with mean annual temperature around minus 50 degrees and hotter coast. And we will see how these different weather are impacting the distribution of the snow bedform and their morphology. So what kind of bedform do we have in Antarctica? We got some sastrugi, which are erosional bedform. They are formed by the wind abrasions on the snow, and they have sand analogs, which are yardangs. So we have an example of yardang here in Egypt. And generally, the sastrugi are way smaller than the yardang. It's only a few dozen of meters long and a few dozen of centimeters high. Then we also have barchans, which are very easy to recognize with their crescent shape, with two horns pointing downwind. They are known to form in environment with limited sediment supply. And we also found them on sand deserts. So this is an example in Morocco, underwater, and even on other planets such as Mars. And again, if you look at the scale, we can see that snow barchans are generally smaller than their sand counterparts. It's only a few dozen of meters long and a few centimeters high. Then if we move on a larger scale, we have the linear dunes. So they're characterized by their elongating crest, straightness, and parallelism, and it's one of the most widespread type of dune on Earth. So you have an example here in Australia, in sand, but other on Titan. And this can be a few kilometers long and large for snow dunes in Antarctica. And we have a lot of other bedforms. I'm not going to go into details for all of this, but the point is that we have a wide diversity of shape and sizes, and that despite having different environments and sediments, we have similar morphology. So the questions that naturally arise is what are the similarities and differences in the formation and dynamic of snow dunes versus sand dunes? And we already started to answer this because we've seen that we have similar morphology, but very different scale. And one reason for this is the difference in the physical property of the materials. And the main difference between snow and sand is the cohesions. We know that for sediments, cohesion can come from biological sources, with microorganisms, for example, or physical sources. And for snow, the main source of cohesion is sintering. So sintering, it's the growth of bonds between grains due to some temperature or stress. And sintering is very complex because it depends both on environmental parameters, so it depends on the wind, the surface temperatures, the humidity, but also on the snow characteristics. So it's depending on the snow grain sizes, for example. And the problem with this is that we got this wind environmental parameter, which are variable in space, but also in time. And the microstructure, it's also variable in space and times. And so this makes sintering very complex to estimate and understand. And that's the main source of cohesion for snow, but we also have similar sources than for sand, like electrostatic forces. We do not have vegetation in Antarctica for snow. So the question is like, how is sintering impacting the dune formations and dynamics? Because we do know that cohesion is impacting the dune morphology. There have been some experiments on clay, for example. So this was this flatbed in a tank in which we put an unidirectional flow, and the clay content was changing, so we were changing the cohesion. And we could see that depending on how much clay we have different type of bedforms. So we got dunes for low cohesions. With more clay, we got some ripples, and with higher clay contents, we only got ripples. But this impact is unknown for snow dunes. So to try to get more insight into this, I've been looking at the barchans and the linear dunes, and more specifically, what I will try to answer today is how are the morphology and migration of snow barchans evolving, and then we'll move on a larger scales to see how snow linear dunes are evolving, and we'll see if we can explain the orientation of the snow linear dunes over all Antarctica using the sand dunes theory. So let's start with the barchans. We've been looking at the barchan at Concordia stations. You can see where Concordia station is. It's pretty much inland, which means that we have low wind speed and low precipitations. We've been monitoring the surface using a camera, and from these images, we've been retrieving the morphological parameter and migration rate, and been looking at the orientation of snow barchan during an event of reorientations. So how did we do that? So we got this near-infrared camera, which is on a tower. There are also wind level on it. And it's been acquiring images from 2017 each hour from August to May. Because between May and August, there's no light. It's totally dark. And it has been acquiring around 35,000 images. So you have an example here of what we're seeing from the camera. I auto-project those images to properly measure the morphologies. And I've been looking at all the images, and I could identify 51 events of barchans. So you can see an example here where the barchans are moving and migrating. And so we figure it's those events of migration, it's around 1,000 images. And on all those images, I identify the barchans and measure their morphology, which means I've been measuring their arm length, their width, the migration rate, and the total body length on approximately 900 barchans. And so what did we see? We got the length ranging from 1.2 to 12.2 meters, a width from 0.4 to 7.5 meters, and horn length from 0.1 to 6 meters. And so we have very narrow range for all of these lengths. But despite this, we can see very different morphology. So here are a few examples. We have ratio between the horn length to the width, which is varying between 0.05 to 1.5, and the body length over the width between 0.2 to 3. So we can see we have various morphology, and this could be the effect of cohesion through sintering. What we're seeing about the migration rate is that it's changing from 0.1 to 3.5 meters per hour. So you get an example here. We see a few barchans, and if you focus on this one, we can see that 4 hours later, it has migrated of its own length. And let's look at a more specific example. At the example I showed you before, where we can see the formation and reorientation of the barchan. So this is the initial stage of the surface. Then there are some transport that starts, and we can see some snow patches start to develop, and even some small barchans, which is surrounded by this red dashed. As time goes by, we got more and more barchans that are being formed. And then the wind direction changes. And as we can see, the barchans are trying to adapt, but at some point, we do not see the shape of the barchans anymore. Their horn has disappeared. And until the wind stabilized, the wind direction is steady again, where the barchans form again and they can pop with and align on the wind directions. And then when the wind direction is steady, they just migrate. And you can see an example of migration here with the line being between each hour. And let's look at the wind data more specifically. So here you have the wind direction during this event, and the color is giving the wind speed, and in red it's the barchan orientations. So we can see that during the first stage, during the formation, the barchans are forming an inner direction which align on the wind, and then as the wind direction starts to change, the barchans are not are not aligned on the wind direction anymore, and this is particularly visible here, where we have some time lag between the wind directions and the barchan orientations, which is t, and alpha is the difference of orientations between the wind and the barchan. And what's really interesting in those events is that this time t can be linked to the morphology and the flux. So we got here the time, which is proportional to the height of the barchans and its width, and it's also depending on the snow flux. So we've been calculating this time for all the events of reorientation we have, and over the 51 events where we can see barchan migrating, we only have 3 events with reorientations. And we've been calculating this time. So we can see here this theoretical time of reorientations versus the measured time of reorientations of the barchans. And overall, it's pretty consistent, but we can see that some points are a bit off. And this is because the flux is depending on the threshold wind speed and the aerodynamic roughness. And we could not measure the flux, so we have to estimate it. And this threshold wind speed is depending on the snow characteristics. So it's depending on sintering, which is depending on the environmental parameter and the snow structure, which are changing both spatially and in time. So this threshold wind speed is not constant, and it's very difficult to estimate as it is changing all the time. And it's the same for the aerodynamic roughness. So we just use rough estimates, but this means that by observing the reorientation of the barchans, but also the migration speed of the barchans, which can also be related to the flux and the height of the barchans, we can have estimations of the threshold wind speed and the aerodynamic roughness. So that's a way to get more insight into the snow properties, and sintering is to observe the dynamic of barchans to get those values. So we've seen that we got barchans that are frequently observed, but sporadically dynamic at Concordia stations. We have a wide diversity of snow barchan morphology, and that we can use barchan dynamics as indicators of the snow transport and the snow properties. So that was the problem with barchan is it's very local. So here we have only been looking at barchan in Concordia, and we cannot look at them with remote sensing because they are too small, which means that the informations we got on the snow properties and the transport cannot be extended to all the continents. That's why we will move on a larger scales by looking at linear snow dunes, which are way bigger and can be observed by remote sensing. And here we will see how do the snow linear dunes at D47 evolve over time. So you can see the location at D47 here. It's close to the coast, so contrary to before, we got high wind speed with a mean speed around 13 meters per second and high precipitations. And so I've been looking at the orientations of the snow linear dunes here and trying to predict those orientation using the sand dune theory. So for this, I've been using all the Sentinel-2 and Landsat 8 images available in the summer from October 2016 to March 2022, because again, during winter, it's too dark. Those images have a resolution of 10 and 15 spatial meters, and this is, you can see the time lapse of the regions of interest, which was evolving, it's not moving anymore. And to get the orientation on those images, we've been using the 2D spatial autocorrelations. So you have an example here of the raw images. You can see the dunes in these directions. We apply the 2D spatial autocorrelation, and we can clearly see the dune direction here. And then we integrate those autocorrelations over a pie slice, basically. And this gives these blue lines. And to get the orientation from this integral, we take the maximum, which is represented in orange. And this maximum gives us the value of the dune orientations. This can also be applied when you have two different dune orientations. So here it's another example. We can see the dunes which is in these directions. So one direction is pretty vertical and the other one is more oblique here. When we apply the 2D autocorrelation, we can see the two different orientation over here and here. And as before, we take the integral, and to get the first orientation, we take the maximum, which is in orange again. And to get the second orientations, we take the local maximum, which is in red. And this is how we can get the two different orientations. Then we compare those orientations with the theoretical sand dune orientations, which relate to formation mechanism depending on the sand availability. So basically, if we have low sediment availability, we are in the elongating mode, and the dune orientations. The dune will elongate in the flux directions, and if we have high sediment availability, the dunes will grow in the directions which maximize its growth rate. So let's look at a few examples to see what it means. To calculate those two orientations, we need to have the flux. And to get the flux, we need the wind. So here you have an example of a wind roses. You can see that the wind is going northeast, and we got mainly speed between 6 to 15 meters. From this wind, we calculate the sediment flux roses, which is in blue. And we have then the orientation. So the elongating mode orientation, it's in brown, and you can see it align on the flux, which is just what we said before. And the bed instability mode orientations, it's pretty much perpendicular to this elongating mode. So that's for a simple unidirectional case. But when we have more complex winds, such as the winds that we have inland of Antarctica, the situation is quite different. So here we can see that we have wind speed between 0 to 9 meters per second, and it's basically blowing everywhere. So we get the flux, and we see that the elongating mode aligns on the north, and the bed instability mode orientations, it's not perpendicular anymore, it's pretty close to the elongating mode. And this was tested on real sand dune fields. So you have here the field orientations compared to the predicted orientations, and it was shown that it could explain the orientation in sand dunes fields, but it was not tested for snow dunes. So let's look at what we have. At D47, this is the monthly directions of the dunes. So in black, we have the first orientation detected, and in blue, we have the second orientations. We can see that the orientations at this location mainly ranges between 120 and 140 degrees. And what we are interested in is the change of orientations. So we are focusing on the time when we have more than a 10-degree differences between 2 months. And we found 7 events like this when we have a change in orientation of the observed dunes. And the question is, what is happening? So if we look at the first event, for example, in 2016, here are the remote sensing images. So we can clearly see a difference between October and November. In October, we can see small dunes that are in these directions. And in November, we got longer dunes, which are different orientations. And the question is, what is happening between those two events? And the problem is that we don't have a continuous time series of images. So we are using the continuous meteorological data from the RERA 5 reanalysis to get more insight into what is happening. So we look at the wind directions. And the color is giving the wind speed. And what we can see is that between those two images, we got wind speeds that can be up to 25 meters per second. And it's generally around 16 meters per second. And if we look at the precipitation, so that's the red curve, it's cumulative precipitations. We have 500 millimeter of water equivalent between those two images. And we can divide this time series into 3 periods. The first one, we got no precipitations and a wind speed around 12 meters per second. The second one, we got precipitations and high wind speed with this event of 25 meters per second wind speed. And we can also note that we have significant amount of precipitation because it's representing 11% of the annual precipitations. And then the last period with no precipitation and low wind speed, which is mainly under 10 meters per second. So I've calculated the elongating mode orientation on all of those periods, and we found that it's consistent when calculating during the precipitation period. But that's only for one event, and we have 7 of them. So let's see if we can make similar observations on the other events. So the time between the two images, it's ranging between 5 to 31 days. And for all of these periods, we could see that we have precipitation and wind, and that those events of precipitation and wind lasted for 30 to 160 hours. And we got significant precipitation for all these events, between 2 to 11% of annual precipitations, which ranges in the top 30% of the most important precipitation event for these locations. And we also see that we always have winds with wind speed between 8 to 28 meters per second. So we've seen that for all the events, we have significant precipitations and high wind speed. And we'll do the same as before. We calculate the elongating mode orientations for all of the gaps. So this is the blue marker. And you can see that it's not very consistent with the new observation observed. But when we're calculating only during the precipitations, we can see that it's consistent except for this one event with the square marker, which is the event where we have the largest gap of data of 1 month, and so it's more difficult to constrain. But we can see that in all the other cases, the elongating mode observations is consistent with the new orientation observed, which is suggesting that the change of orientation is happening during this precipitation event. But we still don't know what is really happening because we have a change in orientation, but is this due to the formation of a new dune system, or is this due to the reorientation of the old dunes? So there's a few indication on this because we have significant precipitation and they represent between 80 to more than 200% of the volume of the new dunes. We also know that we have high wind speed, so we always have transport. And we also see that for most of the event, we can see the old dunes under the new orientations. So all of this is suggesting that we got the formation of a new dune system above the old dunes, which can not reorientate because they are already sintered. So we've seen that we have 7 changes in orientation, which always involve significant precipitation and high wind speed, and that this new orientation probably result from the formation of a new system of dunes. And this means that we got very fast formations of snow linear dunes because it's only taking a few days. So it's faster than for sand linear dunes. So this was for the orientation of dunes at D47. But now let's see if we can apply this over all the continent and if we can explain the orientation observed in Antarctica using the sand dune theory. So basically we'll do the same, but on all the continents. We'll use all the images of November and December of the year 2018 to 2021. Again, it's Sentinel-2 and Landsat-8 images. And to get the orientation, we'll do as before with the 2D autocorrelations. We'll remove the area with crevasses and mountains as they disturb the algorithm, and we will rely on the redundancy of images to reduce the impact of clouds on the orientation's estimation. And what do we got? So in orange, it's a mountainous area that have been removed. In pink, it's an area with crevasses. They are also removed. And what we are left with is this blue area, which is the area where we detected dunes. So basically, we detected dunes everywhere, and actually we detected them over 95% of the study area, which make Antarctica the biggest dune field on Earth. And it also means that we have dunes absolutely everywhere in Antarctica. And if we look at their orientation, so this is the orientations which is given by the correlate in 2013, 2018, 2019, 2020, 2021. And when we look at all those different maps, we see that they're pretty similar. And if we look at their differences more precisely, we have some differences over the ridge here and over West Antarctica and sometimes over the coast. But what we also see is that we have large regions where the orientation is not changing much between all of this here. And that's what we will focus on. We will focus on this persistent pattern. So we look at this map, which is the most frequent orientation detected from 2018 to 2021. And what we see is that we have a contrasted situation between East and West Antarctica, with large homogeneous dune fields in East Antarctica, which are separated by the ridge here, and smaller dune fields over West Antarctica. So to understand those orientations, we'll start by comparing it with the wind to classify them. So we consider that dunes are longitudinal if they are parallel to the flux directions. So we have an example here of longitudinal dunes, and that they are transverse if they are perpendicular to the flux directions. And if you're not used to look at remote sensing images, if you follow my mouse, I can show you here, there's the dunes. You can see another one here and here. And if they're not longitudinal or transverse, they're oblique. So we compare our observations with the flux, and what we see is that most of the dunes in Antarctica are longitudinal dunes, so that's all the black area, and it's more than 60% of the dune detected. So it means that the dunes align with the mean flux. The transverse and oblique dunes are mainly located over the ridge and in West Antarctica. But this does not explain the orientation. So to get more insight, we've calculated this elongating mode orientation and bed instability mode orientations using ERA 5 reanalysis. So you have here the bed instability mode orientation map and the elongating mode orientation map. And when we compare it with our orientations, we see that we can explain 63% of the observed orientations, that we are mainly in the elongating mode, which is the brown area, which imply a low snow availability, and that the bed instability mode and the regions which are not consistent with this theoretical orientations are mainly located in West Antarctica and over the ridge. But overall, this means that over all the continents, we most of the time have a low snow availability for transport. And what does this mean? How can we evaluate the snow availability for transport? So first we need transport, and we know that over the inland, we got low wind speed, we have higher wind speed over the coast. Then the snow, it's coming from precipitations, and we've seen this before. We know that we have a dry inland and wetter coast. So all of this would tend to indicate that we have a low snow availability in the inland. But then snow, it's also disappearing because it's water. And when we got sublimations, we got removal of snow. And we can see that sublimations is the purple regions, it's mainly over the coast, and so that we have very few sublimation over the inland. And it's like an order of magnitude difference compared to precipitations. And the other processes that is removing snow, it's sintering. But as I said before, sintering, it's depending on a lot of parameters that are very difficult to estimate. But what we know is temperatures is governing the kinetics. So we do have access to temperatures, and we've seen that we got hot, coast and cold inland. So that gives us indications on the sintering and is suggesting that we have fast sintering over the coast and very slow sintering over the inland. But the problem is that sintering does not only depend on temperatures, it's also depending on the snow grain radius and microstructures. So this does not mean that we don't have sintering over the inland. It just means that we cannot evaluate it. And so the problem to evaluate this snow availability is that sintering is a key component, but it's poorly constrained. So that's why we need to study dunes, because it's indicating that we have strong sintering all over Antarctica. And so we've seen that linear dunes are ubiquitous and persistent, that longitudinal dunes is the dominant type of dunes in Antarctica, which is similar to Earth desert, that the two modes for sand dune orientation, it's consistent with most of the observation, and it's suggesting low snow availability for transport in Antarctica. And if we go back to our broader topic, we've seen that we got a lot of similarities with the same widespread of the longitudinal dunes and this sand dunes theory that can be applied to snow dunes in Antarctica. However, we also seen that the formation of the new dunes is really fast. It's only taking a few days. And we could not observe migration of the linear dunes, which suggests that they are already sintered. And there is still a lot to do on snow dunes. There are still a lot of questions. And the next steps would be to predict the spatial distributions of the type of dunes. So we can put it into models, or we can also predict the snow characteristic. And there have been some attempts for sand dunes using the estimated sand thickness and the flux direction constancy. There have been some attempts also for snow dunes using the wind speed and the threshold wind speed for transport. But as I said before, this threshold wind speed for transport is really difficult to estimate and to constrain. So these classifications cannot be easily adapted to the different locations. And one key to get more insights into this would be to characterize sintering using the dune morphology. And this could be done using numerical simulations. So what we're having here is an example of the simulation using rescale. So we could map all the sintering in Antarctica using the dune morphology and finally get more insight into the snow characteristic, but also into the snow transport. Thank you for your attentions. And here's the penguins that I've seen in Antarctica. It was not playing with dunes, but anyway.
Thank you very much, Marine. That was a very nice presentation.
Thank you.
So it's now time for questions, discussions. So once again, you can type your question in the chat. You can also raise your hand and speak. That's just in an ordinary seminar. Don't be shy. And maybe I can start with the questions just to show the good example, or maybe JB or Maddie, you have a burning question. Burning from snow is dangerous, but yes, JB, go ahead.
Yes, I do have a question. First of all, thanks, Marine, for a very nice talk. I'm not hampered by a lot of knowledge on dunes or even snow. We don't have a lot of snow here, but I was wondering if you compare it to sand transport. Do you actually see the same processes like siltation and modified siltation and stuff like that, like in sand grains? Do you see that for snow particles as well?
Yeah, we have the same type of transport, but the difference is that sometimes, for example, we got more sublimation during transport, so the snow grain are just disappearing during transport, and it's also impacting the snow surface, and it can increase the cohesions. So we can have like transport that starts, but it's increasing cohesions and slow down. But basically, for the mode of transport, we got saltations, suspensions, and creeping as for sand.
Okay, thanks.
I have a question. Oh no, there is Daniel Novaki has a question. Please.
Hi, thanks. This is very cool, really awesome stuff. Thank you. The barchans stuff I was particularly interested in because I'm doing some work in Alaska using cameras, also not for snow bedform work really, but we get a lot of times where there is sea ice and snow bedforms, including barchans that form. So it's really cool to see this work in Antarctica using cameras as well. I was curious, is there a publication that is either out or soon to be out with this work and the other stuff you presented today?
So there's a publications on the snow linear dunes in Antarctica, which has been out in August. It's widespread snow linear dunes, something. And for the barchan, it's in preparation, so in pretty few months, maybe years, I don't know.
Got it. Thank you.
Thanks for the question. Philippe, do you want to ask yours?
Yes. So of course there is also ice, maybe kind of snow on Mars, right? So would you expect also snow dunes on Mars, and then which size, and so how could we be able to detect them?
But I think there's dunes on Mars, so I don't see why we wouldn't have snow dunes. And then for the size, I guess it would depend on the cohesions there. I don't know much about Mars, but if it's really cold, we would have like less cohesions, but it's also depending on the snow grains. So I don't know. But we do have, there's a publication that has shown that we got these mega dunes like on Mars, which is similar to some type of dunes that there is in Antarctica. They've been seeing them on the North Cap, polar, I don't know, in the north of Mars. But for smaller structures, I guess we just have to wait for the rover to get there.
Yes,
And
because
then,
you were saying that remote sensing is not precise, accurate, or precise enough, right, to get them. I see.
yeah, because they're under 10 meters, and Sentinels-2 is the best resolution for Earth with 10 meters. And sometimes it seems that in some regions we may have barchans because we got like 2 or 3 pixels which look like this, but it's really difficult to say, as it would be like at the edge of the resolution. And the problem is we don't have there's some higher resolutions satellite like Pleiad or Spot, but they are not acquiring all the time. They acquire on demand, and I don't think they will agree to map all Antarctica every 10 days or.
There's a similar question, I think, from Anli, saying, fantastic talk. How do you think your work applies to understanding the cohesion of dunes on Titan? And would it be possible to evaluate with limited data? Any additional thoughts on Titan?
Well, I guess one way would be to do some cold room experiments when we can monitor the cohesions, parameters, and everything, and try to see from what we know from Titan, what parameter would be good, or to use numerical simulation, maybe, once they successfully represent what we see in Antarctica, then we can extend those simulations to Titans. This is maybe more realistic than doing snow dunes in cold room.
Thanks. Any other questions?
I may have another one, but please, all the audience is welcome to ask. Yes, my second question is, what would be, to your opinion, what would be a good analog system to study the equivalent of snow dunes at the laboratory scale? You know that when we want to study ordinary sand dunes, we work underwater, so it's not exactly the same, but some of the features are similar. But then if you want something which basically, have sintering or something close to sintering, what should we use then?
That's a good question, because sintering is, if we think of underwater, we would need some flocculations, kind of particles, but then it's not evolving the same way, like in time and everything. So I don't know what we can use, and that's also the problem, because it would be much easier if we could have smaller dunes that we can reproduce and control, like sublimations and sintering and everything. So for now, I would say numerical simulation are the best, or you need a very, very large cold room.
Yeah.
Thank you.
We have a hand raised from Young Lee. Would you like to ask your question?
Yeah, thanks for a nice presentation. I have a question about, have you ever looked into like long-term changes in snow dune morphology changes, like due to changes in precipitation or surface temperature and so on, whether it's growing in height or decreasing, that may affect the atmospheric dynamics and so on?
So the problem with snow dune is that we don't have the height, for example. And when I was looking at the continent scale, the snow linear dunes over the 10 years, because I've been looking at 2013 also, we could see some regions where it seemed that there was no change in morphology. We don't know for the height, it was probably decreasing due to sublimations, but we could not see on the picture, we could not see any change. But there's a problem again, is that the resolution is a bit too coarse, so we may have missed some structural change. Also, one thing that we do see on high resolution images, like 1 meter resolutions, we do see that sastrugi are generally formed on one side of the dunes. And we haven't looked at long-term data because we need to have those images on demand. But what we're thinking is that we got the snow dunes that is being formed and which is sintering very quickly. So it does not change, like it does not move, but it's being eroded. And the sastrugi are like eating the dunes and eroding it. But in itself, we think that the sintering is too fast for the dunes to migrate or evolve. But that's for Antarctica. And maybe it could be interesting to look in other regions like Greenland, where we have more precipitations. Also, we have higher temperatures. So for sintering, it's not clear how it will look.
Thank you.
Thank you for the question. Maybe we'll just have one more from Lucas, and then we can wrap up. Go ahead, Lucas.
Yeah, thank you. Thank you for the nice talk. It was really interesting. A little bit of a follow-up to Ji-Young's question. In the classical Barchan fields, we often see the often described mechanics of dunes passing through other dunes, or the carving of fresh dunes from the horns of Barchans, for example. Have you seen these kind of mechanics in the snow dune fields as well?
Yeah, I have some example in Concordia where we can see some barchans passing each other and colliding, but the problem is like often, most of the time, the event is not long enough, so you will just see one barchan colliding into another, and then the wind stop, and the barchans sinter, and they are not remobilized. So it's not clear like what is happening, but also it's still there's a lot to do with those data. It was at the end of my PhD, so I did not have time to look in all of this. So it's probably happening also, but I cannot like really tell more about this.
Okay, thank you.
Excellent. Many
Thank you.
thanks. Many thanks, Marine, for the excellent talk, and many thanks for all who tuned in and joined and joined the discussion. Yeah. Mary, would you like to close off? Please, some last word.
Sure. Yes, thank you again for a wonderful talk, and to everyone who was able to join today. The final edition of the ISAR 2024 newsletter is going out in just a few weeks in December. It will be announcing the career award winners. So please head over to our website to make sure that you've created your new ISAR account and have your membership up to date so that you're receiving our newsletters and other community updates. If you have any questions, you can always reach us at the admin@aeolianresearch.com. That email address is also on our website, which Marine is showing the address there at the bottom left. Thank you very much. So thanks again, and hope to see you all in just a few weeks for our next talk. Thank you.
Bye, everyone. And thank you, Marine, again.